Hi, everyone, and welcome to today's webinar on hydrophilic interaction liquid chromatography, or HILIC. Today, we'll explore the fundamentals of HILIC, how it works, when to use it, and why it's become such a powerful tool for analyzing polar and ionizable compounds. So whether you're new to HILIC or looking to optimize your method, I hope you'll walk away today with clear, actionable insights. So let's get started. So here's exactly what we'll cover today. We'll start with a bit of context, introduce the Shodex brand, how HILIC fits into the broader chromatography landscape. Then we'll explore when is HILIC most useful and the advantages it offers. And then after that, we'll dive into method development tips and real-world application examples using our columns. So before we dive into the science, let me introduce Shodex. Shodex is the HPLC column division of Resonec Corporation. We specialize in polymer-based stationary phases for over 50 years, and we manufacture all of our compounds entirely in-house in Japan. We're best known for our size exclusion and sugar analysis columns, but our lineup also includes columns for reverse phase, ion exchange, and of course, HILIC. And we serve a wide range of industries. So whether you're quantifying sugars in dairy, mapping peptides, or separating PFAS in water, Shodex has a column solution that can fit your needs. So here's a quick look at what makes Shodex columns unique. Unlike traditional silica-based columns, Shodex uses polymer-based stationary phases. So our polymer gels are custom made with starting with the monomers like styrene or vinyl alcohol, and then we fine-tune things like pore size and particle size and cross-linking to fit specific applications. And then we apply surface modifications like sulfonation, amination, or carboxylation to create different separation modes. We offer over 300 column products, but today we'll focus on our HILIC line, which includes ligand types optimized for sugars, peptides, nucleotides, and even PFAS. So let's take a closer look at how HILIC actually works. So HILIC is short for hydrophilic interaction liquid chromatography, and it's a technique designed for separating very polar analytes that don't retain well on reverse phase column. So in a typical HILIC setup, you have a polar stationary phase and a mobile phase that's mostly organic, usually 70 to 90% acetonitrile. Even though the mobile phase is mostly organic, there's still a small amount of water present, and that water forms a hydration layer around the stationary phase surface. And this is where the retention happens. There's two key mechanisms at play here. One is partitioning. So analytes move back and forth between the mobile phase and the water-rich layer on the stationary phase. And two is interaction. So while in the hydration layer, analytes undergo hydrogen bonding, electrostatic interactions, and van der Waals forces with the polar functional groups on the packing material. And the right-hand portion of this slide highlights that analytes with stronger polar character interact more intensely with the hydration layer and are retained longer. So the less polar compounds don't interact as strongly and elute more quickly. So let's talk about core advantages of using HILIC. So first and foremost, HILIC is perfect for compounds that are far too polar to retain in reverse phase chromatography. And secondly, HILIC operates with high concentration of organic solvents like acetonitrile, so it's extremely well suited for LC-MS detection. The high acetonitrile enhances ionization efficiency in electrospray sources, which leads to better sensitivity. HILIC methods also tend to be more MS friendly overall. There's no ion pair reagents required, and mobile phases are often simple and volatile. So if you're analyzing polar or ionizable analytes, HILIC gives you retention, resolution, and MS sensitivity in one platform. So when should you use HILIC? So use HILIC when your analyte is too polar or charged to be retained on a C18 column. This is especially common for molecules like saccharides, sugar alcohols, phosphorylated metabolites, amino acids, and nucleotides. One quick rule of thumb is check the analyte's log P, which is a measure of a molecule's lipophilicity. Analytes with a log P below 0, meaning they're highly polar. So these compounds tend to elute near the void volume in reverse phase, but are well retained in HILIC. So here's a closer look at the Shodex HILIC column lineup. Each of our columns, our HILIC columns, are built on a polyvinyl alcohol base support, or PVA, and this provides excellent chemical stability and supports a range of functional group modifications. So first we have the VC50, features a carboxyl ligand, ideal for peptide separation via weak cation exchange and hydrophilic partitioning. Next, we have the VN50, which uses diol-based ligands designed for polar compounds such as oligonucleotides, oligosaccharides, and hydrophilic molecules. Next, we have the VG50. It's an amino-functionalized column with a blocked ligand, ideal for saccharides and sugar alcohols. Next, we have NH2P50. It's also a polymer-based column with primary amine ligands, ideal for reducing sugars under alkaline conditions, and it's overall a versatile choice for general HILIC applications. And lastly, we have the VT50, which contains a quaternary ammonium ligand and supports retention of those ultrapolar and anionic compounds, such as glyphosate or short-chain PFAS, through combined HILIC and anion exchange mechanisms. So each column is designed to target a specific retention mechanism and analyte type, giving you a broad toolbox for method development. So let's walk through a simple framework for developing a HILIC method. Before diving in, it helps to ask a few guiding questions like, what are your target compounds? What detection method will you use? And do you have any system constraints? Once you've clarified that, the most important parameter to start with is the acetonitrile content. A good starting point is 80% acetonitrile with 20% aqueous buffer or just water. From there, you can refine things like pH, buffer strength, and other variables like flow rate and temperature. So in the next few slides, we'll break these parameters down, starting with the organic content. So here we're separating dextrin oligomers using a VG25 column. The mobile phase is a mixture of water and acetonitrile, and we're modifying that acetonitrile ratio slightly across these runs. So as we decrease the amount of acetonitrile from 1 to 3, or we increase the amount of water, or yeah, retention decreases and the peaks begin to coalute. So this shows a classic feature of HILIC. High acetonitrile equals higher retention and better resolution. So if you go too low on acetonitrile, the separation disappears entirely. So selecting the right starting point is crucial when building your method. So here we're taking a closer look at how adjusting the acetonitrile percentage affects HILIC retention. So we have 3 compounds with varying polarity: inosine, phenylalanine, and tyrosine. All 3 of them have negative log P values, meaning they're fairly hydrophilic and ideal candidates for HILIC separation. So what you're seeing in the chromatograms is the effect of increasing the acetonitrile content from 50% up to 90%. So as the acetonitrile percentage increases, retention increases dramatically, and so does the separation. And this is due to the stronger partitioning into the water-rich layer on the polar stationary phase. So at higher acetonitrile contents, the mobile phase becomes less polar, and so analytes spend more time in that hydration layer and interact more with the stationary phase. Now, if you look at the retention plot here, you'll notice something important. It's not linear. There's a sharp increase in retention between about 70 and 90% acetonitrile. So that's the zone where selectivity and resolution really improve and your analytes start to spread out more cleanly. So that's why optimizing the acetonitrile content is one of the most critical parts of HILIC method development. Too little acetonitrile and your compounds will coalute, and too much acetonitrile and you may start to see broader peaks or even issues with ionization and LCMS workflows. So in most cases, the sweet spot for HILIC separation is somewhere around 75 to 90% acetonitrile, but this can vary depending on the column and the chemistry of your analytes. So now let's take a look at how gradient method can be used in HILIC. So just like in reverse phase, gradient elution in HILIC helps you separate complex mixtures, but the solvent behavior is reversed. So we're starting here with a high percentage of acetonitrile at 88%, which promotes strong retention of polar analytes. And then we decrease the acetonitrile content over time to 60% to gradually elute those more strongly retained compounds. So in this example, we're using a Shodex VG50 column to separate a mixture of 15 saccharides ranging from small monosaccharides like ribose and arabinose and to larger oligosaccharides like raffinose and multitriose. So looking at the chromatogram, you can see the HILIC retention trend in action. The smaller sugars like the monosaccharides are eluting first, while the larger sugars, the oligosaccharides, elute later. And this is due to the increased hydrogen bonding and polar interactions with the stationary phase as sugar size and polarity increase. So generally, a more negative log P for longer retained species is observed. So using a gradient like this is especially powerful when you're working with complex mixtures that span a wide range of polarity and molecular size. So now let's take a look at how buffer concentration affects retention in HILIC. So in this example, we keep the acetonitrile content fixed at 70% and vary the concentration of ammonium bicarbonate in the aqueous phase. So on the graph, you can see that the retention time decreases as the buffer concentration increases. And why does that happen? So that's because the higher buffer strength introduces more ionic species in the mobile phase, which compete with the charged analytes for ion exchange interactions on the stationary phase. So this suppresses the electrostatic retention and causes analytes to elute earlier. You can also lose some resolution at as the buffer concentration increases, which is another reason why ionic strength is a key tuning parameter in HILIC. So now let's take a closer look at why buffer concentration affects retention by understanding the column chemistry. So many HILIC columns are functionalized with charged groups. This diagram shows the VT50 base material, PVA support with quaternary ammonium groups, and these create a positively charged surface that supports multiple interactions. So in addition to hydrophilic partitioning, we get ion exchange behavior layered on top. And this is where the buffer strength becomes critical. So at low buffer concentrations, there's fewer ions in the mobile phase, and that means analytes can more easily interact with the stationary phase, leading to stronger ionic retention. But at high buffer concentrations, the mobile phase is crowded with competing ions, which block those interactions, so the retention decreases. You'll also get more retention when the analyte and stationary phase are oppositely charged, so understanding the charge state of both components is essential when tuning your method. And this dual mode retention, partitioning, and ion exchange adds another layer of selectivity in HILIC, especially useful when working with compounds like amino acid, phosphorylated metabolites, and nucleotides. So next, let's talk about how pH influences retention in HILIC. We tested the same set of sweeteners under different pH conditions, alkaline and neutral, on a Shodex VG50. So at alkaline pH, we observe a strong correlation between the log P and the retention time. In this case, the more polar analytes, those with lower log P values, are retained longer. So that tells us that hydrophilic partitioning is dominant under alkaline conditions. The stationary phase is deprotonated and there's minimal electrostatic interaction, so retention reflects how well each analyte partitions into the water layer. And now looking at the neutral pH, here's where things shift. We see an increase in retention in aspartame, the purple trace, and acesulfame, the blue trace, even though their log p values haven't changed. And this suggests that there's more going on than just polarity. What's happening is electrostatic or mixed mode interactions kicking in, possibly due to a change in the analyte charge state or the ionic character of the stationary phase. So this is a good example of how neutral pH can favor ionic retention, especially when you're working with partially ionized compounds. And although it's not shown here, let's talk about acidic pH. In acidic conditions, amino type columns become protonated, forming protonated amine groups. And this allows them to attract negatively charged analytes, so retention increases for acids. At the same time, acidic analytes may lose their charge and basic compounds can become positively charged, leading to electrostatic repulsion and reduced retention. So the takeaway here is pH can dramatically change the charge state of both analytes and the column, which shifts the balance between hydrophilic and ionic retention. Flow rate is a simple but powerful parameter in HILIC. This example on the VG50 column clearly shows how flow rate tuning can improve peak separation without changing the mobile phase or the gradient. So as we lower the flow rate from 1 ml per minute to 0.3 ml per minute, we increase the interaction time between analytes and the stationary phase. This leads to greater retention and sharper resolution, as you can see in the pink trace at 0.3 ml per minute. Of course, the trade-off is a longer runtime, so in practice, it's about finding the right balance between speed and resolution based on your analytical goals. And temperature is another key parameter in HILIC method development. So raising the column temperature, as we see here, from 30 to 60 degrees Celsius, reduces mobile phase viscosity and improves mass transfer, which helps sharpen peak shape. But at the same time, retention decreases. As analytes diffuse faster, they spend less time interacting with the stationary phase, shifting peaks earlier. So temperature can be used to fine-tune selectivity or shorten run times, but always consider column stability and detector sensitivity when making adjustments. Injection solvent matters a lot in HILIC. One of the most common issues in HILIC is poor peak shape, and it often comes down to the sample diluent. So in this example, the mobile phase is 80% acetonitrile, but when we inject the sample dissolved in pure water, the mismatch causes peak broadening and splitting, and the theoretical plate number drops. And that's because the sample solvent disrupts the equilibrium of the water layer and on the stationary phase, and this disrupts the analyte retention and focusing. So this simple adjustment can make a big difference in retention, resolution, and reproducibility in HILIC. And this slide reinforces that point about injection solvent compatibility. So even if your analyte concentration is low, the wrong sample solvent can dramatically affect peak shape. In this experiment, sugars were dissolved in pure water and the same amount of analyte was injected at different volumes. As injection volume increased, peak shape deteriorated and theoretical plate number dropped. And that's because a large water plug entering a mole phase that's mostly acetonitrile disrupts the equilibrium of the stationary phase, leading to poor focusing and broader peaks. To prevent this, your sample solvent composition should closely match the mobile phase. Ideally, you would want the final solution to contain at least 50% acetonitrile. And if high water content is unavoidable, the next best option is to minimize your injection volume. To ensure consistent retention and good chromatography, always consider sample matrix effects in HILIC. And now let's talk about how column material impacts HILIC performance. So silica-based HILIC columns are widely used, but they have limitations like narrow pH range and silanol groups that can cause peak tailing or poor recovery, especially for reducing sugars and basic compounds. The Shodex VG50 column, on the other hand, uses a PVA backbone with bonded amino groups. It's stable from pH 2 to 13, fully compatible with 100% aqueous and 100% organic solvents, and free of silanol groups. So you avoid secondary interactions and get cleaner, more consistent peaks. So in the chromatograms, the VG50 clearly outperforms the two silica-based amino columns, especially for glucose and mannose, which show distortion on the silica columns. So this really highlights the strength of polymer-based HILIC for a stable and reproducible separation. And here's a real-world example of HILIC for oligonucleotide separation using the Shodex VN50 column. So we're looking at the synthetic DNA ladder from a 2-mer to 60-2-mer. On the top, chromatogram shows the full mix. The 60-2-mer elutes as a sharp peak, and below are the extracted ion traces for each size fragment. The VN50 is built on PVA base with diol functional groups promoting hydrophilic partitioning. Because oligos are highly polar due to their phosphate backbones, they interact strongly with the water layer on the stationary phase, so longer strands retain longer. So this is a pure HILIC mode, no ion exchange, making the method simple and highly reproducible. We're using a linear gradient with 50 millimolar ammonium formate, a volatile buffer that's fully LCMS compatible. And the result is a clean, length-based separation, perfect for QC, purity checks, or fragmentation analysis. And this slide highlights how versatile the VG50 column is for HILIC application. So in one run, we separated a mix of amino acids, organic acids, and saccharides. We used a linear gradient starting at 80% acetonitrile and decreased to 10%. That high organic content boosts retention through partitioning into the hydration layer. As water increases, compounds elute based on polarity and interaction strength. Detection was done with ESI in negative mode, which is ideal for acidic and polar compounds. The VG50 column is PVA based with amino functionalized ligands offering a highly hydrophilic surface, good hydrogen bonding and electrostatic interaction, and has strong retention for small polar analytes. It's stable from pH 2 to 13 and fully LCMS compatible, making VG50 a reliable choice for complex samples in food, clinical, or metabolomic workflows. And this is a great example of how HILIC excels where reverse phase struggles, especially with ultra short PFAS. So we use the VT50 column to separate highly polar compounds like TFA, DCA, and these usually elute near the void in C18 methods, making detection very difficult. But in HILIC, it's polarity driven. So the longer chain PFAS like PFOS and PFBS elute first, while shorter, more polar ones like MCA and DCA retain longer. And that's because the more polar the compound, the more it interacts with the hydration layer on the stationary phase. And VT50 uses a PVA backbone with quaternary ammonium groups, supporting hydrophilic partitioning and weak anion exchange. So this dual mode retention helps even the smallest PFAS separate cleanly. And in this method, it uses 50 millimolar ammonium bicarbonate, and at 30 to 70% water, and it's an isocratic mobile phase. Detection was done by ESI in negative mode, and no ion pairing was required. So this is a robust LCMS compatible solution for short chain PFAS monitoring in environmental and regulatory testing. So before we wrap up, I want to leave you with a few practical tips to help you get the most out of your HILIC separations, especially when using polymer-based Shodex columns. So first, you always want to run the C of A method that comes with your column. It confirms performance and gives you a solid benchmark before running any of your own samples. Second, allow enough equilibration time. HILIC columns need slightly longer time to stabilize because of the high acetonitrile content and the formation of the water-rich layer on the stationary phase. Third, match your sample diluent to the mobile phase as best as you can. And fourth, go easy on protic solvents like methanol. Small amounts can improve peak shape, but too much can disrupt the water layer and affect retention. And finally, prep your mobile phase carefully. Use high purity solvents, filter and degas everything. Make sure your buffer is fully dissolved, especially in high acetonitrile conditions. And these simple steps can go a long way in improving reproducibility, retention stability, and overall method robustness. So to summarize, HILIC is a highly effective technique for separating polar, hydrophilic, and ionizable compounds. It works by using a high organic mobile phase, typically high acetonitrile, and a polar stationary phase, creating a system where polar analytes are retained through partitioning and hydrogen bonding. It's especially valuable for compounds like sugars, amino acids, nucleotides, PFAS, and small metabolites, many of which are elute too early or not at all in reverse phase LC. And now, why choose Shodex for HILIC? Shodex HILIC columns are built on polymer-based technology, which means a wider pH stability, no silanol groups, so you get sharp peaks even for basic analytes, and we are fully LC-MS compatible with no need for ion pair reagents. We also offer dedicated columns tailored for specific analyte types, as discussed. And Shodex has over 50 years of experience in polymer column development and delivers highly reliable and performance-driven solutions for modern HILIC workflows. So if you'd like to learn more, the best place to start is our website, shodexhplc.com. There you can search by compound, explore application data, and download valuable resources like our full catalog, column manuals, and technical notes. So whether you're developing a method or checking column compatibility, it's all just a few clicks away. And for our US users, online pricing and credit card ordering are available once you register, so it's fast, easy, and convenient. And of course, we're here to support you beyond the webinar. Our team is based in New York City, where we operate an in-house lab equipped with the HPLC using UV and RI detection. We also maintain local stock shipped directly from Japan, so we're ready to help you quickly and hands-on. We offer a trial column program so you can test the method before committing, and you can even send us your samples. We're happy to run them in the lab. We also provide site visits, Zoom or team consultations, and fast responses via support@shodexhplc.com.